All right, we're going to look at this particular first function here. This was in the homework. What does this function represent? Well, we know there's an invariant point here, and there's no other invariant points. We also know this particular graph doesn't touch the x-axis because we don't have any vertical asymptotes. Now I'm going to show you the equation of this function. Here it is. This equation is the equation of a reciprocal function. Which reciprocal? This one down here. This denominator down here is a parabola. Its vertex is at 2, -1, and this particular parabola has a negative value in the front, so it means this parabola must open downwards. Alright, so how come that blue graph is our inverse? Well, let's go over the different understanding. All the values here, the y values, are negative. In the reciprocal function, the graph remains where it's negative, remains negative. So all the points here on the blue graph are negative because all the points in the original function were negative. Next, if you notice, the blue graph here is decreasing. In the same interval, the black graph is increasing. When you take the reciprocal of a function, it changes from increasing to decreasing, or from decreasing to increasing. And that's what's happening here. This is decreasing while this function is increasing. From here point on, original function is decreasing, so our reciprocal function is increasing. Alright, on to the next part. Given a function such as this, what's your automatic instinct to do? I'm hoping you're saying to factor this. So you factor it, factor the numerator, factor the denominator, and lo and behold, you see something. You see something that affects the domain. So you need to state the restrictions. Restrictions are part of your domain. So I'm just going to write it out as follows. So, how do we get all these answers? Let's go back a step. So, here we have our restrictions. Well, how does that help us? Well, if you notice that I cross out the x plus 3 in the graph, in the equation. Why? Because we have an x plus 3 on the top and the same x plus 3 on the bottom. So top will cancel with the bottom, so that you're left with 3x minus 3. Well, how does that affect our restrictions? Folks, the restrictions stayed the same because this is not our original function. It's a simplified version. Our original function is up here. So, this simplified version means that x equals 3 is still a vertical asymptote, but at -3, what we do is we plug it into here and we find out that the value here is not 0, not some undefined number anymore. There's no 0 in the denominator. So, when I plug in that value of -3, I get a hole at -3, -1/2. So the graph of this function will have a hole at those values. Let's look at the graph. So the asymptote of that function, there's a vertical asymptote at x equals 3. So we draw that out. There's our x equals 3. And we're just quickly sketching it, folks. When you do it on the test, make sure you have proper scale showing. So 3, and we need to test a point to the left and to the right of the vertical asymptote to describe the behavior around the asymptotes. So, how do we test for behavior around the asymptotes? Well, we use a table of values. We use a table and pick a point very close to 3. So I'm picking 2.999. Remember, we always use the very small number smaller or slightly bigger than the number we're looking at for instantaneous rate of change? Well, folks, in here we use that same 0.001 to find a number really close to the asymptote to prove to us what's happening. So I plug in 2.999 and into the equation. There's the equation. And I get negative 3,000. Then I'm going to plug in 3.001 into the equation. And I get a number like positive 3,000. How does that help us? Well, it helps us state the behaviors around the asymptote. For example, as x approaches 3, now that's too much writing there, folks. So let's go backwards a bit, just so that you have seen it. As x approaches 3, y approaches from the negative side, so 3 from the negative, so 3 from the left. You will get the y values approaching negative infinity, because when I plugged in a number really close to 3, I'm already getting a very large negative number. We then do it again for this thing. What does this say? Well, as x approaches 3 from the positive side, so from the right side, we're looking at y approaches positive infinity. That is the description of the behavior around the asymptotes. Next, you have to start graphing this. We have some points. In fact, we have the y-intercept, which is an important feature. The y-intercept, when you plug it in, is negative 1. So 0, negative 1 is going to be our y-intercept. There it is, folks, right here. These arrows here refer to the direction on either side. I'm just going to erase this as part, just so that we can look at our graph without seeing anything behind it. I'm just going to graph that red part. There we go. Let's see what the graph does now. Well, we know it's going to hit at 0, negative 1. And we also know that there is going to be some sort of hole, folks. The hole is going to be at negative 3 and negative 1/2. So we draw our graph. Now, is that the end of our graph? Hopefully you're saying no, because on this side we need to have a graph because we have an end behavior. So pick values on this side. My recommendation is that you pick values close to each other. So we picked 4 and 6. 4, 3, and 6, 1 fit over here, so we draw our graph accordingly. Now, let's look at another question. Looking at the following, what can you tell me about this function? Hopefully, some of you are thinking already in terms of asymptotes. You know there's got to be probably a horizontal, maybe not, maybe a vertical asymptote. What is it that there's going to be? Hopefully you're remembering that a restriction is either vertical or, the restrictions state that there must be a vertical asymptote or a hole. So in this case, nothing canceled away, so that x equals 1 is a vertical asymptote. Now the domain of this function is affected, if you remember, from the reciprocal. So what we're going to do is we're going to stop the video and come back to this page on the next video, just so that I spend one video on working with something called oblique asymptotes. Alright, see you on the other side.